All right, welcome back. Now, let's talk about annuities and how to find the value of an annuity. Now, an annuity is a retirement vehicle. It's something that pays out regular payments. So you basically save up a certain amount of money, a large sum of money, and the idea is to take equal number of payments over a period of time and of the same amount. Okay, so that's what we call an annuity. Okay, so let's look at this formula. So first of all, we start with the formula of a compound interest. So this is like for compound interest, and what we're going to do is, this is the future value. This is a lump sum principal deposit or investment, and then R is the rate, which is as a decimal. Okay, and then T is time in years. Okay, and so if we write this out, so over a certain number of years, like for example 3 years, it would look like this. Oops, sorry. Forgot T equals 0. So what happens here is compound interest formula works like this. The first year, or the zero, when you begin, you only have the principal, that's all. And then after the first year, now you have the principal plus the interest, right? This is where this 1 plus R. So you get your principal back plus your interest rate based on R. And then after year 2, then you got this interest rate, right? So this is your beginning balance at the beginning of year 2, and at the end of the year 2, then you're going to add this amount, which is basically this times 1 plus R. And then you add, at the end of the third year, you add this amount plus 1 plus R. So you're adding more interest, right? So this is your principal. This is the amount of interest after year 2. This is the amount of interest after year 3. And this is the amount of interest added plus, principal added after year 3. Okay? And so now, the common ratio, as you can see, is 1 plus R. So this is a geometric series, right? So if this keeps going, right, we have a geometric series where what? A1, the first term is P, and the common ratio R. Now, R, don't get confused. Instead of R, because R here represents the interest rate, not the common ratio. So I'm just going to write common ratio. So the common ratio is 1 plus R. So now if we wanted to get the nth partial sum, right? So remember the formula for the nth partial sum. Okay, so in this case here, the nth partial sum is going to be S sub n equals, and remember the formula, A sub 1 times 1 minus R to the nth Now here, this is the common ratio, not the interest rate. So we just got to be careful because we're using the same notation. Okay, so remember that's the general formula. This R represents the common ratio. Okay, but remember the common ratio is this. So when we replace things, we're going to get what? A1 is P, so we get P times, and then this is going to become what? It's going to become 1 minus the quantity. Now the common ratio is 1 plus R. Right? And then down here, this is going to become 1 minus 1 plus R. But N N is going to be T, right? Because it's a positive integer, but in this case we're dealing with years. So in this case we're replacing N with T. Okay? Now if we simplify this a little bit, we get right? Because if we distribute the negative sign, we get 1 minus 1 minus R. The 1's cancel and we get negative R. Okay? Now, let's add a number of compounds because this is based on compounding per year. Notice every year it compounds. That's what we mean by compounding. Every year you're adding interest. Right? But what if we want to add different compounds? What if we want to compound weekly? So this would be annual. But what if we want a more general formula where, hey, what if we want to compound every week? Or if we want to compound every month? Right? So how many compounds per year would that be? So if we're talking about weekly, that would mean it'd be compounding how many times per year? 52. If it's monthly, it'd be 12. If it was semi-annual, that would be 2 because every 6 months. If it was quarterly, that would be 4, and the number of compounds would be 4. So now what we're going to do is we're going to add N, but in this case, remember, N in this case represents the number of compounds per year. Okay? So what are we going to do? How are we going to do that? Well, in order to do that, we have to divide the interest rate by the number of compounds because we have to divide the interest rate over the number of compounds over the year, right? So what we're going to do is all we have to do is add the N. So we're going to take the interest rate, the annual interest rate, and we're going to divide by N, but then time also has to match the compounding because if it's annual, then T has to be the number of years. So what we're going to do is we're going to add it to make the time match, right? So if this is going to be monthly compounding, then we've got to have the exponent represent the number of months. So in order to do that, we're going to multiply the T, which represents the number of years. That doesn't change. But we're going to add a factor in the exponent N, which is then if we take T times N, that gives us the total number of whatever. If it's months, N is 12, it'll give us the total number of months over the whole life of the investment, okay? Okay, so if we do that, then what happens is the formula becomes this. So S of N becomes what? It's going to be P times 1 minus the quantity 1 plus R divided by N right? Raised to the what? T times n power divided by negative r over n. Now, what we could do is to get rid of this negative sign, because we don't like to have that negative in the denominator. So what we're going to do is we're going to multiply, we're going to take the negative here, put it at the top, because we can move the negative around, because this is just negative 1, right? So whether it's negative here, and then what we can do is distribute the negative through here. And so we can simplify this and get our final answer, which is going to be P. And then we're going to switch these, so it'll be 1, the quantity 1 plus r divided by n raised to the t times n power minus 1 all over r divided by n. And so this becomes our formula for finding the future value, right? The future value, which means this is not just a partial sum, but this is the future value of the annuity. So we just derived the formula for finding the future value of an investment, or excuse me, the future value over time of an investment. Okay, so now we're going to do an example where we can apply this in an application problem.